6.2, which is volumes found by rotating a region about an axis or a given line. Well, we've already dealt with area, and when we have nice, pretty geometric shapes, we can use these nice, pretty geometric equations. Well, volume is 3 dimensions. So we're going to be using a base area times a height. This area is 2 dimensions. The height gives us that 3rd dimension. Well, we're going to look at one in particular. We're going to look at the cylinder. When we try to find the volume of a cylinder, we know that it's going to be that base area times that height. Well, that base area is just a circle. The area formula for a circle is pi r squared. That height, of course, we're going to use whatever that height they give us, which is h. So these little cylinders, you've got those circular base areas. So no matter how I would slice it, so let's say it's a salami. I'm hungry right now. So when I make these slices, notice all of these base areas are going to be the same size circle. The radius is always going to be the same distance. And then that height, you just take those slices and add them up. Well, not everything is going to be a nice pretty cylinder, which means those slices aren't going to be the same. Let's look at this little picture right here. We're going to find this area just like we did the last couple of days. We're going to be given a series of equations, and we're going to graph them, and we're going to find the area that is bounded by those equations. So we're going to find that region that's bounded. So that's how we do this guy right here, that area. What's different is now we are going to spin this about the x-axis. So this 2-dimension shape is going to become a 3-dimension shape. So when I spin this, because I'm spinning it about a line, what's going to happen is this little triangular area is going to be a cone. Now when I slice it, make these slices, those slices are still going to be circles, just like with the cylinder. The problem is these slices aren't going to be the same size. If I make a slice down here by the tip, by the point, that's got a smaller radius than this last final slice. Okay? So the problem is the radius is not stationary. But that's okay, because if I go from the x-axis out, that's going to be the radius. That radius is just that function. Okay? So that function was f of x. So that radius changes, so that means I'm going to be using a function so that my radius can change. That'll allow this to be a taller or longer radius than this next slice, then the next slice, the next slice. Okay? Now what we're going to do is we are going to make all those slices, okay, and you definitely want your pepperoni cut from this end because you're going to have a bigger piece than if you're at the right end. But that integral is going to take care of your height. So that x2, x1, that's actually your height. Okay? So when we rotate this about the x-axis, the first thing that we're going to do is we are going to realize that now when we are rotating it about the x-axis, we have no choice. Everything is about the x. So when you rotate about the x-axis, everything is about x's. What's inside your integral has to be x's. Your endpoints or your limits here, those have to be x's. When we set up our integral, we're going to take that base area, so that pi times our radius squared, that's our base area. But remember, our radius changes. So because that radius changes, we have to put the function in there. So it's pi r squared, so it's got to be pi f of x squared. So this gives us our 2 dimensions. This gives us our third, because this integral takes care of the height. This right here takes care of our base area. So we're still doing base area times height. It's just our height looks a little strange. Okay, so this base area are going to be all those circular slices. That height is going to add up all of those slices. All right, so let's see what this is going to look like. Find the volume when rotated about the x-axis, and you really want to make sure that you're paying attention to which axis or which line you are rotating that about. So all I did in my calculator is I graphed y equals the square root of x. Now they've told me that I'm going from 1 to 4. So I just widened my window here. My window is from 0 to 5, but I'm only going to be looking at from 1 to 4. So this is the area that I'm going to be rotating about the x-axis. Now what's important about this area is that it sits directly on the x-axis. So when I rotate this about the x-axis, we are going to get a solid figure. Okay. So when I do that rotation, I'm going to form these nice pretty little circles. I'm going to have these little circular slices. Okay. Okay, so I've got these nice little pretty circles. I tried to change that and it's just not working for me. All right, so I have these nice pretty little circles. So I get this solid piece, okay? This nice little solid piece. Seeing how we're getting close to Christmas and I'm still hungry, it's going to kind of look like a ham. It's going to be a nice solid circle. So that volume is going to equal, okay, the base area is going to be that pi. My radius, which depends on the square root of x, okay, because here that radius is going to be bigger than down here at the very beginning. So that radius is going to change, so it has to be a function. So square root of x squared dx, so pi r squared, and then my height, we're going from 1 to 4. So you've got the 2 dimensions inside. You've got your third dimension coming from your integral. Okay? Now, if you have to do this by hand, and they will ask you to do it by hand, you're going to pull the pi out, and you're going to simplify. Well, square root of x squared is x, and then you're going to integrate. You're going to do x squared over 2. You're going to put the 4 in first, and then the 1 in, and you're going to simplify. So when I simplify that, I'm going to get 15 pi over 2. Now, if you get to use your calculator on this, I want you to get in the habit of pulling that pi out. So if you use your calculator, I want you to pull the pi out. Remember, it's a coefficient, so you can do that. You can either simplify or leave it as the square root of x squared. Your calculator doesn't care. So you'll put this in your calculator so that you can change that back into a fraction, and then you'll multiply that by pi so that you can get the same pretty answer by using your calculator as you do from doing it by hand. So I'll be pulling that pi out in front so that I can put it in my calculator and things will look nice. All right, so let's look at another example. Once again, they're going to give us all of this starting information. I am going to graph it and find out where that area is. X equals 1, x equals 4, and then the y equals 0 is the x-axis, and then you have your 1 over x, so you get this area here. Okay. Once again, that area sits directly on the x-axis. So when I rotate that about the x-axis, and I always put that little curly there so you can see we're rotating it about the x-axis, you get solid circles. So you get a little figure that looks like this. It's kind of like a megaphone, only it's completely solid. So each of these little slices are going to be full-blown circles. And once again, you want to be on this end this time. You want to be on the left end to get the bigger slice. I'm going to pull out that pi. So I still have pi r squared. My radius is going to be that function, 1 over x. And then my height is going from 1 to 4. So 1 to 4. Okay. So just looking at what we have listed here, this is my radius squared. That's pi, of course. And then this guy is my height. So we've got all the pieces there. So when I put it in my calculator, save the pi for later so that you can multiply your answer by pi and get a nice pretty fraction. So when I take the integral from 1 to 4 of 1 over x squared, I get 3/4. So my volume is going to be 3 pi over 4. That's our volume, and it is in cubic units. Okay, let's look at another one. When I look at 3, I've got y equals 1/2 plus x squared, y equals x, and then going from 0 to 2. So when I graphed this, here's my 0 to 2. So when I make my little picture here, my area is this little piece right here. So when I rotate this about the x-axis, notice this doesn't sit on the x-axis. So that means I'm going to have a hole here. So this isn't going to be a solid piece like the last two examples. This is going to be a hollow piece. So it's going to look like a vase. So notice my little circles here. There's an open area in here. So this is going to go directly like this. Okay, so all of these pieces are going to have a hole in them. Well, they have a special name for that, of course. They call that the washer method because what you have is a piece that looks like a washer. I think since we're using pi, we should have called this the donut method and just keep it a pastry like Fiesta. So, but they called it washer because they named it way before I was born. So when we look at this washer, I need to cut out this inside piece. So in order to create a washer, you have the bigger circle, which that radius would be that red line. You're going to cut out that smaller circle, which would be that green guy. So when I do that, I am literally taking big circle minus little circle. Okay, so I've got to come up with my formula. Well, my area of a circle is pi r squared, so they both have pi, so I just factored that pi out in front. F of x, that's going to be that bigger radius. That's going to be the function that's on top. G of x is playing the part of that little circle. That's the guy on the bottom. Just like with our area, top function minus bottom function. Now we do have to be careful because we are talking about a big circle minus a little circle. So notice it's f of x squared minus g of x squared, not this guy. Do not f of x minus g of x and square that. Because here you've got big circle punching out little circle. Here you've got big radius minus little radius. So you have small radius. You just have a circle. There's nothing being punched out there. So using that washer method, I can see that this top function is my f of x. This bottom function is my g of x. So when I set that up, I'm still going to take the pi out in front because I want to have the ability to make this into a pretty fraction. My f function is this guy, 1/2 plus x squared. So there's the f squared minus the g squared. I'll put it in parentheses just so it feels special. dx. Okay, so here is my f of x, and then this is my g of x. Okay. Now, when I'm looking at my interval is going to be much the same as it was before. It's going from 0 to 2. Notice my slices start here at 0 and they go all the way to 2. So 0 to 2. When I plug it in my calculator, I just need to make sure I'm putting those parentheses around my 1 plus or 1/2 plus x squared. I don't need the parentheses around my x. So really, if you're plugging that in your calculator, if you make sure, whoopsie, if you make sure you have this guy in there, you're going to be fine. Okay. So when you plug that all in your calculator, you get 69 pi over 10. Now we have to be careful when we draw our area. Is it all smack dab against the x-axis, or is there space in between? If there's space in between, you're going to have a washer. So let's look at another example. Here's what they give us. Y equals x squared and y equals 9. So I've got this nice pretty little picture. Here's my shading. Pretty shading. When I look at this, notice I am not sitting directly up against the x-axis. I have all of this open area here. All of this is open. So if I were to spin this about the x-axis, I would have this tube. It looks like a tube on the outside, but on the inside, it's going to have that V-shaped hollow area. Okay, so you're going to be missing a cone on the inside here and a cone on the inside there with that vertex touching in the middle. Okay, so from the outside it looks solid, but on the inside you've got yourself washer-like slices. So when I find that volume, I'm going to take that pi out. I know that it's the top function, which is that 9. And I'm going to subtract that bottom function, which is my x squared. Okay, so that top function was my 9. That bottom function is my x squared guy. So I'm going from top to bottom, top to bottom. Now I need to know what my points of intersection are here and here. They didn't come right out and tell us this time. You can guess looking at this example, but if you have trouble guessing, go ahead and set them equal to each other, because y equals x squared, y equals 9, that means x squared has to equal 9. And then square root both sides, you get a plus and a minus 3. So we're going from negative 3 to positive 3. Okay, so you put that in your wonderful handy dandy little calculator. Oh, you get a very nice fraction. 1944 pi over 5. Okay, so you're looking at that area. When you rotate it about the x-axis, if it isn't all smack dab against the x-axis, you're going to have a washer. If it sits directly on the x-axis, you're going to have a disc.